Okay, number 12 in section 10.5, we're going to determine the convergence or divergence. They say, or state that the test is inconclusive of the given series. Now, when they say the state that the test is inconclusive here, they're saying that there's no test that shows that it's is conclusive, or no test is conclusive in determining the convergence or divergence. Basically what we're wanting to do here is go over all the tests that we have. And so remember the summary for tests that I have, the table that summarizes all our um, series tests, I guess, for convergence or divergence. Here's the power series we're looking at. And I'm looking at the first one, which is the nth term test for divergence. Let's take a look at that. What's the limit as n goes to infinity of the terms we're adding up? Well, that goes to zero. Clearly, the denominator, we've got polynomial functions in the numerator and denominator, and the denominator degree is greater than the numerator degree, so this is going to go to zero. Again, remember, that tells us nothing about this series, right? That, right, nth term test cannot be used for convergence. Only if this limit is not zero can we conclude that it is divergence. So it is divergent. So we don't know yet whether this series converges or not. Okay. So next thing is, geometric or P series. Well, clearly it's not geometric and it's not a P series, although, kind of looks like I could, compare it maybe to a P series. Certainly not integral test. I would not want to integrate this particularly. Um, and so I'm going to use a comparison test. I'm actually going to end up using limit comparison, and I'll show you why. So uh, I'm going to compare to a P-series, and how do I do that? Well, if I take the highest degree term in the numerator, highest degree term in the denominator, I get this thing, which simplifies down to this. So I'm going to compare it to this series, right? And well, the terms that come from this series, I guess. And notice we know this is a P series. If I factor out the 1/3, this is a P series, P equals 2, so it's convergent, right? Remember our P series tests, right? If the value of P is greater than 1, it's convergent. Value of P less than or equal to 1, it's divergent. So what I'm going to use is limit comparison because trying to get direct comparison here is a little tricky when I'm comparing these, because the numerator on the left is a little bit bigger because it's plus 8n compared to, just n squared, which makes this one on the left a little bigger in general for n, at least the numerator. But the denominator here has a plus 7, so this denominator here makes the fraction over here a little bit smaller just looking at the denominator. But the interaction is overall what's for various values of n, which is going to be true. So instead of doing a direct comparison, we will go right to a limit comparison. So remember, limit comparison has looking at any series, of course, positive term series, actually, greater than zero. Take the limit as n goes to infinity of the ratio of these terms. Now, granted, the terms may be equal to zero for some values of n, but eventually we got to have some value k, so that from k on, they're both non-zero. And then we look at the limit of this ratio. If that limit is some positive number, then we know the B sub n's converge, the one we're comparing to, then our series A sub n converges, right? This is the convergence column. And then similarly, if we get that same positive limit, but B sub n diverges, then they diverge together. So we don't have to do the comparison, the direct comparison like here, get this inequality to come out. So when we do limit comparison, I compare the terms from the series we're adding to this one, dividing by a fraction, right? Multiply by the reciprocal, distribute this 3n squared out, and we get this. And then clearly, I think the degree of the top and bottom are the same. And so the limit is going to be 1, right? It's going to be 3 divided by 3. And so by this point, going through these, we've looked at these limits so many times. I expect you to be able to go right to the limit. Again, if you having trouble with that by this point, let me know. We talked about using L'Hopital's rule. We talked about dividing by n to the 4th here and simplifying. Either way, you get a limit of 1. But that's important because that limit is positive, which by the comparison test means that both of these series either converge together or diverge together. Since I know this one, right, is convergent, I know that my series also converges. And in fact, it converges absolutely because, again, if I take the absolute value for n greater than or equal to 1, I just get the terms of the series. It is positive term series, right? They're positive. Um, okay, so that's this one. Nice little problem to analyze and look at using limit comparison. Okay, hope this helps.